Good morning, everybody. It's a great pleasure to me to present to you Daniel, someone who I met for the first time a long time ago when he was a PhD student under the supervision of Luis Serrano and Manuela in the very nice city of Valencia. Daniel, thank you very much for being with us today. And I know that you have been teaching a lot. You must be very tired, and you are very kind to accept my invitation. Thank you very much, Daniel. And just to present you, Daniel, I have made a brief academic trajectory, and he got his bachelor in chemistry in 2003 in University of Valencia, and then a master in chemistry 2005, and in 2009, he got his PhD in chemistry in the University of Valencia, working with Manuela Merchan and Luis Serrano Andres. And this is an important aspect because Manuela Merchan, for those who are interested in applications of CASPT2 methods in organic and nucleobases and this kind of subject, she was, I think, the person who started working with this subject in the early 90s. And Luis was her student at that time. So they are, among others, in Valencia, I can say the founders of this subject in working with CASPT2 and organic molecules. So we must say thank you to Manuela, and unfortunately, Luis is not among with us. It's sad, but that's life. And then from 2010 to 2020, he was in Uppsala with Roland Lind for a postdoc period. In 2013, he went back to Valencia and joined the group what they call quantum chemistry for the excited state. And since 2017, he is the single group leader of this very good group working with quantum chemistry of excited states. Daniel has also a lot of awards and prizes, and I selected some of them. The first one is the very prestigious fellowship, Marie Curie, for his postdoc in Uppsala. And in 2014, he was supervising Purria Farahani. Purria was in São Paulo a few years ago, and Purria was awarded the PhD student work, and Daniel was his supervisor in that time. And in 2017, he got a tenure-track researcher, Ramon and Cajal Fellowship. And I mean, if this is the most prestigious fellowship in Spain. And in 2018, he got another prize called the Quantum System in Chemistry and Physics, Promising Scientist Prize from the International Society Centro de Mecânica Ondulatória Aplicada. And among his research interests, I highlight computational biochemistry and bioluminescence, molecular basis of DNA and RNA reactivity and photochemistry, luminescence and no radiative decay mechanisms in optoelectronics, excited state chemistry and physics of mercury in compounds. So it is also very interested in atmospheric chemistry. He develops and implements methodologies to study non-adiabatic process. And he is author or co-author of two softwares, Multispec and Multispec Sol, that the main of these softwares are simulate absorption and emission absorptivities in solution and in gas phase, the subject of his presentation for us today. And just a few numbers. He is author of around 100 publications with about 1,900 citations, several chapters in book, and age index 25. So during this seminar, please keep your microphone off. I'm sure that you are going to enjoy this seminar, and if you want to make any questions, you can interrupt. Just raise your hand in the Google Meet screen. There is an option to raise your hand. Just raise your hand, and I'm going to see that you want to place a question. So enjoy. I'm sure that it will be a very, very nice talk. Thank you very much, Daniel, for being with us. I'm going to stop my presentation now.
Thanks to you, Antonio. It's always very nice to discuss with you, and also some friends from the same university. Eric, I saw Eric Bastos also joined the meeting, no? And
yes.
I know also Willie. Yeah, hello, Eric. How are you?
Also, nice to see you, Daniel.
Yeah, nice to see you too. Yeah, send regards to Willie also. Okay, let's put the presentation. Okay. Antonio, you see it now?
Yes, you can see it. You can put it in full screen if you want.
Please, anything is happening, if you don't hear me or whatever, just let me know, okay?
Okay. You can put in the full screen if you are presentation mode, if you wish.
Sorry?
You can put in the presentation mode. Yes, okay, now it's good.
This is fine, right, now?
Yes,
so I will proceed unless you stop me, okay?
Okay.
So good. Well, this presentation, the context of this presentation is the quantum chemistry of the excited electronic states, that, as you know, is the interaction between chemical systems and light, and chemical transformation that occurs upon absorption of light, or the other way around. So chemical reaction giving rise to light. So this is the context more or less of this presentation. That has this is a field that has many applications in biology, medicine, technology, and atmospheric chemistry. And during the last decade, we have carried out some research in this field in order to understand the mechanism, for example, of the photoisomerization of retinal, that is responsible for the process of vision. I'm showing here this illustration. We also studied the photochemistry of DNA and mechanism of repair the lesions, as Antonio was introducing before. Then we also were interested in determining the mechanism of bioluminescence and chemiluminescence. Also try to improve or design molecules that can be used in photodynamics therapy in the treatment of cancer. We have been also doing research trying to understand how solar radiation is interacting with atmospheric pollutants, in particular compounds of mercury. And we also did research on with applications in nanotechnology, in particular trying to improve or to design materials with luminescent properties. So excited state chemistry, the first step in the excited state chemistry, of course, is the absorption process. So light is arriving to a chemical system, and then the system is absorbing, it's interacting with the light, and it absorbs the light. So photochemical reaction, the first step is the absorption process, as this is very important in photochemistry, the absorption process. As you can see here, for example, in this equation, that is relating the rate of a photochemical process with the quantum yield of this particular excited state chemical reaction, the absorption cross sections that I'm showing here, this sigma, and the irradiance of light. So you can see that if we want to quantify the efficiency of a photochemical process, we need good estimations of these properties, in particularly quantum yields and absorption cross sections. So it's very important to try to have methodologies or to characterize properly these two magnitudes. So I will focus in this presentation in these two magnitudes and present methodologies based on multi-configurational quantum chemistry to obtain these numbers. So first approach to quantify or to obtain information about the intensity of the absorption by a chemical system is what I call here the single geometry approach, in which we take a molecule, isolated molecule in gas phase. We optimize the ground state, the equilibrium structure of the ground electronic state, and at this geometry we compute the vertical excitations and the associated oscillation strengths. This is the first approach to have an idea about the absorption properties of a chromophore. And here I'm showing the picture that we would obtain in this case, this mercury compound. So in this single geometry approach, we will obtain these sticks in red, in which the vertical axis is the oscillation strength, and this is the energy position of the transition. So by this approach, we will get this. This is okay as a first approximation, but in many cases, we need to go beyond this single geometry approximation and try to consider the nuclear sampling of this chemical system in the ground state. We need to consider that at room temperature, this molecule is vibrating. So we need to consider the vibrational aspect. And by this means, we will obtain a much better picture. So we will move from oscillation strengths to the determination of cross sections that I'm showing in this part. And I'm representing the cross section by the magnitude sigma. Okay, this is important to go from this approach to the other approach. Is important in many situations, and I'm showing here two examples. One case is this compound. So if you use the first approach, single geometry approach, we get this information for the first excited state of this molecule. So this stick with a oscillation strength of 0.00472, and this is the intensity, absorption intensity for the first excited state. But the reality is this one. The first excited state has an oscillation strength much higher. And what is happening here is that if we optimize the ground state structure, the first excited state has this nature, means the electronic transition that is involving only the O-NO part of the molecule, the transition between these orbitals. And then, if we consider the vibrational characteristics of this system at room temperature, then what is happening is that we have other geometries that are possible, not only the minimum, and then some of these geometries has an excited state that is characterized by another nature of transition, of electronic transition, as I'm showing here. So in this case, we have contribution from the bromine part, and then this increases the intensity of the transition. So if we want a more quantitative or more accurate description of the intensities, we need to go beyond the single geometry approach. Another example in which it is quite interesting to go beyond the oscillation strength and the single geometry approach is when we have not uniform irradiance, as in the case of the solar radiation, in which the irradiance is a function and is not constant. And then, so in these cases, we need a function of the absorption intensities as a function of the wavelength. So we can integrate together this and produce a good number of the rate of the photochemical process. So these are just two examples that are, see, yeah?
There is a badge in your screen called derived de compartir, ocultar. If you
okay,
sorry. Yes, we will see it better.
Okay.
Okay.
Now,
thank you.
Yes, thanks for letting me know. Let me see. I was here, right? Yeah. So good. So in order to obtain or go beyond the single geometry approach, there are two methodologies that are quite good, that are based on quantum dynamics and what they call here normal mode approach. With these methods, we can obtain the cross sections even and also the raw vibrational structure of the electronic bands. The first approach is a time-dependent approach to obtain the absorption cross sections, and is based on the fact that in quantum dynamics we are obtaining a magnitude that is called the autocorrelation function. That is this overlap between the wave function at the beginning projected in the excited state and the wave function at time t. So this autocorrelation wave function that is computed in the quantum dynamics is related with the absorption cross sections by this formula. And then, so in quantum dynamics, we obtain directly the spectrum, the absorption spectrum. The problem is that this is quite challenging and very time demanding for practical applications to run quantum dynamics. And then it's only limited for a few excited states, mainly the first excited state, and in small systems, relatively small, and not very complex conditions. The second approach is the normal modes approach, in which what we do is to obtain the second derivatives, I mean the vibrational structure of the ground state and also the excited states that we want to characterize. Then we can use a harmonic approximation. We will obtain the vibrational structure and then the vibronic couplings. And with this, we will have a raw vibrational structure of the absorption bands and also the cross sections. Here, this approach normally is used with time-dependent DFT because we need second derivatives, and it's quite complex or difficult to implement if we want to characterize many excited states. And we have excited states with crossings, conical intersections, single, triple crossings. So the complexity or the application of this approach becomes a bit challenging. And as I said, normally this is used with time-dependent DFT, but in some situations we need to go beyond single reference methods because we have problems with multi-configurational nature. And I'm showing here two examples. The case of the mercury compounds, and in particular, if we want to characterize the absorption of many excited states in these systems. Here we need to work with all electron basis sets. We need to take into account the relativistic effects, spin orbit couplings, and to consider high order excitations, double, triples, etc. For instance, in this mercury oxide, some of these bands have contributions from almost 50% of double excitations and beyond. So it's important to have a wave function with multi-configurational nature. Another example is the electronic structure of DNA radicals. In this, I'm showing here two of these radicals. This is uracil nucleobase, and this is the OH radical that is produced upon attachment of this OH to C5 position or C6 position of uracil. So if we use here time-dependent DFT, the absorption wavelength for these two radicals are basically the same. So there is no distinction between them, and if we use CASPT2, then we see that the absorption properties are clearly different. So we need also CASPT2 or multi-computational quantum chemistry to get a good description of the absorption processes in these radicals and to see which of these radicals is present in the experiments that are carried out in a solution of uracil that is irradiated with high energy light, able to break the OH bonds of water. So these experiments, what they do is to break the bonds of water in a solution in which we have uracil. So then experimentally OH is produced, and they determine experimentally this spectrum. But it is not known if this absorption band is related to this radical or this radical. So by means of theoretical methods, we can try to assign this band to either this one or this one. So we will see at the end that we can reproduce the absorption spectra of these radicals and have a assignation of the spectra to one of these radicals. Okay, in order to improve also the determination of the absorption intensities, it's important to note that in some cases the chromophore is in solution, or it can be in interface between, for example, water molecules and gas. It can be inside the protein, as in this case. It can be in the surface of inorganic material, or embedded in the DNA. And this environment is going to affect the absorption properties of the chromophore. So if we want to get an accurate picture of the absorption properties, we need to consider the interaction or the effects of the environment. First approach to do that is to use reaction field models in which we put the chromophore in a cavity, and then the environment is just approximated as an dielectric continuum. We use a dielectric constant that is able, well, is approximating the effect, the overall effect of the environment. But this is quite simplistic picture and is not considering the dynamical and statistical effects of the solvation. If we want to consider this and go beyond this simple picture, we need to take into account the conformational space of this macromolecular system, in which many different structures can be accessed at room temperature. We need to do a conformational sampling, and we can do that with molecular dynamics or Monte Carlo. And then we need to also methodologies that accurately treat the interactions between the chromophore and environment. I just put here 3 of them: QMMM approaches, average solvent electrostatic potential approaches, and density embedding. So, okay, the aim of this work that I'm presenting here is to choose a computational approach that is able to predict with enough accuracy absorption cross-sections and molar extinction coefficients. This magnitude is mainly used, as you might know, in gas phase, and this one in condensed phases, in solution mainly. So we want to have a computational approach that is general enough. It means that we want to deal with a large number of excited states. We want this approach to be able to be applied to mono and multi-computational problems, and try to see if we can apply it to all the elements in the periodic table. We are interested in band line shapes that can be achieved by nuclear sampling of the chromophore. We want to consider also the conformational sampling of the environment, and to take into account, of course, the environment effects in the electronic structure of the chromophore. So that's the computational approach that we want to have in order to apply it to different problems and to obtain these magnitudes with enough accuracy. So this is the first goal, and the second goal is to benchmark this approach. We will use as molecules for benchmarking acrolein and one mercury compound. Then we will apply to other mercury compounds with unknown absorption properties. We will see examples of application in luminol chemiluminescence, and also in the case of DNA radicals. So let's see first the computational approach and the computational approaches that we will calibrate, we will benchmark, and the results of this calibration. So the first approach that I'm showing here is in the gas phase. So, and it's based on four steps. Is well-known approach, this one. For example, you can have a lot of information in this paper from Crespo, Otero, and Barbati, and in other papers also. So the first step of this approach is to optimize the ground state geometry of the molecule and compute the frequencies. With this information, we will sample the geometries of the ground state using a Wigner distribution that is able to capture the 0-point vibrational energy. So we take into account the quantum effects in the ground state. And then with this sampling, we are obtaining many geometries representing the ground state vibrations at room temperature, for example, or any other one. And then for all these geometries, we will compute the vertical excitation energies and associated oscillation strengths. And with this set of discrete points, we will transform them into a continuous function of the cross sections by using this formula that are explained in details in this paper. So, okay, if we follow these steps, we will get, for example, in this system, mercury bromide, we get this picture that I'm showing here for the absorption cross sections. In continuous lines, we have the calculated spectrum, and this, the dice line, represents the experimental measurements. So you can see here that mainly we are reproducing the main features of the absorption cross sections, and we have a slight underestimation of the intensities of the absorption. So in this case, I'm showing here the case of acrolein, the lowest line excited state of acrolein that is represented by this illustration. Lowest line excited state of acrolein corresponds to a n-pi star excitation, an excitation from the lone pair, mainly in the carbonyl part, to the pi star orbital. In this slide, I'm showing the application of different nuclear sampling techniques in order to obtain the cross sections, the absorption cross sections of this lowest line excited state. So I'm showing three approaches for sampling the ground state nuclei: molecular dynamics, ab initio molecular dynamics, and Wigner distribution that I already showed before in the previous slide. So here we have a classical treatment of the nuclei. Here we have quantum treatment of the electrons and classical treatment of the nuclei. And here we have a quantum treatment of the nuclei in the ground state. Okay, so with these three approaches, we get a number of geometries, and then at each one of these geometries, we obtain, as before, the vertical excitation and oscillation strength. And with this formula, we achieve the cross sections. Here we have the absorption cross sections that we get. In red, we have the molecular dynamics approach. Here in green, we have the ab initio molecular dynamics. And in blue, we have the Wigner sampling. we can see that one feature that is interesting here and has been observed by many other groups is that when we use the Wigner sampling, there is the broadness of the band is much higher. So we have broader bands as compared to the sampling or to the spectra generated by molecular dynamic sampling or ab initio molecular dynamics. Another interesting feature that we still don't know very much what is the origin of this feature is that in the case of ab initio molecular dynamics, we have much higher intensity, and in molecular dynamics, much lower. And in Wigner's sampling, we have a situation in the middle that it's closer to the, in this case, is closer to the experimental band. Okay, so I present here now the computational approach that we are testing for condensed phases. And the first one is based on a sampling of the chromophore, of the nuclei of the chromophore, also using molecular dynamics. So we have molecular dynamics Boltzmann sampling. So what we did here is to run a molecular dynamics simulation using parameters coming from DFT for the chromophore and tip 3P for the water molecules. So we ran a molecular dynamics long enough, few nanoseconds, and then we obtain from the production zone several geometries. Then we compute the vertical excitation energies and oscillation strength, and with this formula we achieve this spectrum. In this case, in the case of the sampling based on molecular dynamics, we obtain this absorption spectrum that I'm showing here in red. This is the case of acrolein in a box of water. And in black, we have the experimental absorption spectrum. Second approach that we were using in these conditions is the QMMMD dynamics, in which now we are using ab initio molecular dynamics for the chromophore and MM for the water molecules. We do the same here, same approach, and we obtain, in this case, the green line that I'm showing here. And the last approach that we are testing is the one that is based on the Wigner sampling of the chromophore. And this is a bit more complex as compared to the gas phase, because here we need to introduce also the sampling of the environment. So what we did is to design a computational approach based on previous information from this paper also. That is based on the following steps, 7 steps. First, we optimize the geometry of the chromophore and compute the frequencies, and using the nearby molecules of water in this optimization, and using also implicit model PCM for the other water molecules. So then we have a geometry optimized for the ground state. We obtain the Wigner sampling for this geometry, and then we fix this geometry and we run a molecular dynamics in order to sample the other water molecules, all this box of water, with a fixed geometry of the chromophore. Okay, then in the production zone of this molecular dynamics, we take several snapshots, and then we introduce all the nuclears, all the Wigner geometries obtained in the step 1. By this means, we will have together the sampling of the chromophore and the sampling of the environment. We will have 100 to 100 geometries representative of all this system. Then we will compute the vertical excitation energy and the oscillation strength, and with this formula also we obtain the molar extinction coefficients. In these cases, for Wigner sampling, the outcome that we get is this one, in dark blue and light blue. So these are the absorption spectra that we get with Wigner sampling. As you can see, as before, as in the case in the gas phase, by the way, sorry, we have two examples of application of this strategy using different softwares, Amber and Material Studio. So that's the only difference between these two cases. Yeah. So what we observe also as before is that the width of the band, of the absorption band, is higher in the case of the Wigner sampling as compared to the other strategies for sampling the chromophore and the environment. Also, again, we observe a high intensity absorption in the case of ab initio molecular dynamics and low intensity band for classical dynamics, molecular dynamics, and Wigner sampling produce absorption intensities in more or less in the middle, much closer to the experimental findings or observations. So, okay, it seems that Wigner sampling is quite good enough, no? And what is positive from the Wigner sampling is that we are considering the 0-point vibrational energy. We have kind of quantum effects treated in the ground state, but something that is lacking is the anharmonicity, because we are using a harmonic approximation. This is something to be improved, yeah, of course. We have applied also this strategy with Wigner sampling to an interface in which we have again here the acrolein. This is a box of water and this is empty space. So we use simulated annealing here in order to find the most stable or the stronger interaction modes at the surface, and then we change the chromophore geometry by the Wigner sampling geometries. We got in this way again 100 to 100 representative geometries of this system where we compute the energies and the oscillation strengths. We obtain this picture for this situation, the interface between water and gas phase. This is the absorption band in water. This is the one in gas phase. And here we have the absorption band that we get for the interface. So we can see that in the case of the interface, we have the main features, all the features of the gas phase, and we have shoulder here at high energies that corresponds to those geometries that have stronger interactions with the water side. So we have a situation more or less in the middle between gas phase and water conditions. Okay, so these are the computational strategies that we have more or less tested. And then we will apply now the one that is based on the Wigner sampling in 3 examples. The case of the absorption cross-sections of mercury, the chemiluminescence of luminol, and the absorption of DNA transient radicals. In the case of mercury, let me start by an introduction of this this problem. So mercury is a pollutant that is emitted into the atmosphere in the form of elementary mercury. Once there is reacting immediately with, well, it's reacting mainly with bromine radicals to form this mercury 1, its oxidized form. And then it continues reacting with many compounds that are present in the atmosphere to produce this mercury 2 species. So this is 1 oxidation step and 2 oxidation steps. These species are more soluble in the water droplets from the clouds, more soluble than elementary mercury, and then they are deposited back into the surface of the Earth by means of the rain. So the lifetime in the atmosphere of mercury 0 is in the orders of months to years, and in the case of the oxidized species, the lifetime is days to weeks, because, as I told you, they are dissolved in water droplets, and then they are deposited in the form of rain. So in order to understand the interconversion between these species and the transportation in the atmosphere and the position of mercury, I mean the cycle of mercury in the atmosphere, the scientists have used computers in order to simulate these processes. And so they are creating what are called atmospheric models that show this kind of results. So they simulate the transportation and the position of species in the atmosphere. And these models are based on all possible chemical reactions, the rates for these chemical reactions, and also the concentrations of the pollutants in the atmosphere. What is happening in the case of mercury is that the predictions coming from these models, atmospheric models, are in disagreement with the measurements around the planet. So it seems that the models are predicting a large amount of oxidized species as compared to those of as compared to the amount of mercury, elementary mercury. When we measure around the planet the amounts of mercury 0 and mercury 2, there is a higher amount as compared to the predictions of mercury 0. Then we try to give an explanation to see what's happening here and see how we could find the reason for that, for these discrepancies between simulations and the measurements around the planet. And we suggested as a hypothesis that solar radiation interacting with the species of mercury could have an important role. And this interaction between solar radiation and mercury species was not taken into account in the conventional atmospheric models. So what we did is to compute the absorption cross-sections of all possible all atmospheric mercury species present in the atmosphere, and then we found that there were many cases with significant absorption of solar radiation. Also, we observed that in the excited state, the bonds that are between mercury and these species becomes very weak in the excited state, and it means that they are prone to photo-reduce back to the mercury 0. Then we considered that this possibility in order to improve the atmospheric model. So this was the previous atmospheric model, and not considering the interaction with solar radiation, and this is the improved model considering the interaction with light. You can see that these colored bands correspond to the prediction from the modeling, and these dots are the observations or measurements around the planet, and this corresponds to the amount of mercury 0. You can see that in the measurements there is more amount of mercury 0 as compared to the predictions from the simulations. When we consider this process of photoreduction, we move from this picture to this picture, and you can see that there is a much better agreement with the measurements. We also continued exploring the interaction of these species with light, and we saw also that this radical is able also to absorb efficiently light, solar radiation, and photoreduce back to mercury 0. And the rates for these processes are competitive with those of the oxidations. In order to improve even further this model, what we did is to try to get more accurate numbers of the quantum yields of these photochemical processes. Okay, so as I remember you, the formula that I was showing at the beginning of the presentation, to compute the rates of a photochemical process. And here we have the quantum yield and the absorption cross-section, and this is the irradiance. So we have strategies. I have shown strategies to obtain a good estimation of absorption cross-sections, and now what I'm showing here is how to obtain good estimations of the quantum yields of these processes. So we used the program Shark from the group of Leticia Gonzalez with CASPT2 and CASPT2, and we ran Benitio molecular dynamics in order to obtain these yields. By this means, we could create a chemical model of the interconversion between all the mercury species. Now we have information about which excited state photochemical paths are present when solar irradiation is affecting these species. No? So we have this chemical picture with all the yields, and with these yields we can recompute the rates for the photochemical processes, compare them with the ground state oxidation reactions, and then what we saw is that in all the cases, at the end, all the oxidized species are coming back to the elementary mercury via the interaction with light, via the photoreduction paths, as I'm showing here. This is the main conclusion that we got in these studies. We have been continuing studying these species, the absorption properties, but now I'm showing the absorption spectra when in solution. So previous information was for gas phase, that is the most representative in the atmosphere, but now we are interested in what is happening when these species are interacting with water droplets from the atmosphere. So what I'm showing here is a systematic study of the absorption intensities in different solvents. Well, this is gas. This is with ethanol. I mean the same species, mercury bromide in ethanol, and this is in acetonitrile. And these are the absorption spectra. So what we can see is that the lowest lying electronic band is shifted towards the red when we increase the polarity of the solvent. And this is also observed in the experiments. We have been attributing this red shifting to this fact, to the distance between bromine and mercury. As you can see in the gas phase, we have a 2.395 angstroms. This is that distance. When we move to ethanol, we have 2.506, and in acetonitrile, we have 2.512 angstroms. So there is a correlation between the red shift and the distance between bromine and mercury. So in conclusion, for this group of studies, what we can say is that sunlight is increasing the lifetime of mercury, and as a consequence, this means that mercury is going to be deposited at larger distances from the anthropogenic sources, I mean emission sources. That's the main conclusion that we get from this group of studies. Let's see now the group of applications of this methodology that I have presented in the case of the luminol chemiluminescence. Luminol, as you know, is the compound that is used in forensic science in order to detect traces of blood. Luminol is shown here. This is the molecule. And in alkaline conditions, with hydrogen peroxide, luminol can decompose to produce this phthalate plus light. This process represents the chemiluminescent reaction of luminol in aqueous conditions. And this process is catalyzed by the M group of blood. So that's why it's used for detecting traces of blood, because the intensity of light is going to depend on the amount of this item. Luminol chemiluminescence is not only happening in aqueous conditions, it can also happen in dimethyl sulfoxide. And in these conditions, the luminol itself, in alkali conditions, can react directly with molecular oxygen, as I'm showing here, to produce light. Few years ago, we studied the mechanism of this complex process, and I will summarize here. So here we have the luminol molecule. The first step is the protonation to produce this D-anion that is strong enough now to activate molecular oxygen. So we have a electron donation to molecular oxygen, and then is activating this species that can react with luminol, forming this endoperoxide bicyclic compound. This is happening via a single triple crossing with enough efficiency. Once we have this bicyclic species, nitrogen can go away, and we arrive to this monocyclic endoperoxide that is the one responsible for the chemical excitation. We have from here on three possibilities of evolution. The first one is the thermal decomposition, in which this bond is broken, and we are producing this species in the ground state. Second possibility is the chemical excitation to a n-pi star excited state. That is a dark state with a conical intersection quite close in energy, and then the outcome of this evolution is radiationless decay. We don't have light emission here. Light emission is happening if this bond breaking is happening with a lot of kinetic energy, so we can populate an excited state of pi star nature, and then in the excited state what we saw is a proton transfer from the amino group to the carboxylate group, producing this species that is the one responsible for the chemiluminescence of luminol. This species is the one that is decaying, irradiating light at 440 nanometers. What is interesting here is the experimental observation that depending on the solvent, we will have a band, chemiluminescent band, peaking at different wavelength. For example, this is the band in dimethyl sulfoxide solvent, and this is the band that is observed when the chemiluminescence of luminol is happening in aqueous solution. So we have a shift from around 500 nanometers to 420. In order to understand what is the origin of this shift, this discrepancy between water and dimethyl sulfoxide, DMSO, what we did is to study it with computational chemistry, both with time-dependent DFT and CASPT2, and we focus on the proton transfer that we observed in the previous study. So what we did is to compute the energy of the excited state upon increasing the distance between nitrogen and hydrogen and approaching this hydrogen to the oxygen. And here we have the picture that we get when we do this study in DMSO or in water.
There is a question.
I hear.
Hi, Daniel.
Yes.
How did you select the number of explicit solvent molecules in this case?
Yes, we first, well, we did in this example molecular dynamics simulation in order to see what is the first solvation shell of this of luminol, and based on that we found that this is a reasonable number. But we did also computations with 1, 2, 3, 4, 5 molecules of solvent, and so we stopped at 5 because it was converging the results also.
Okay, thanks.
Okay, so I let's see. 2017. Good. So I was explaining that we were determining the energy of the excited state along this coordinate, this reaction coordinate of proton transfer from the amino group to the carboxylate group. And we saw that in DMSO, the most stable species in the excited state is the imino form, as I'm showing here. It's more stable than the amino form. And this is contrary to the situation in water, in which the amino form is more stable than the imino form. So there is a difference in the excited state in these two conditions. Then what we did is to compute the emission properties in solution with water and DMSO, and we found this result, these findings. So you can see that in DMSO we have an emission that is redshifted as compared to the emission band that we obtain from in solution with water. Then we can clearly interpret the experimental observation that I introduced before. Okay, finally, and very shortly, I will show you some results about the application of these strategies for computing absorption intensities in DNA transient radicals. I already presented at the beginning these two species, the radical obtained upon attachment of OH to uracil in the C5 position or C6 position. We computed the absorption spectra in gas phase and water. Gas phase is the line that I'm showing here in red, and the one for water solution is this one in green, and here we have the experimental band. So we can see this is the band, this is the band for this species. Okay, the bands that are responsible or that are originated from this species are appearing at much higher energies as compared to these ones. So by these determinations, what we could conclude is that the radical generated experimentally when water is irradiated and is breaking the OH bonds to produce OH radical. So the radical generated is this one, not this one. So now we can tell the experimentalists that what they are observing is this species. Okay, in summary, we have seen here strategies that can be used in order to go beyond the picture that we get from oscillation strengths. We have seen how to move from F values to sigma values or epsilon values. Sigma, the absorption cross-sections in gas phase, and the epsilon, the molar extinction coefficients in condensed phases. We have seen benchmarks in the case of acrolein and mercury bromine, and then applications in unknown mercury compounds with unknown absorption properties, the case of luminol chemiluminescence and the absorption properties of DNA transient radicals. Let me finish this seminar with thanking my collaborators in some of these studies. Also the group of Valencia, the quantum chemistry of the excited state, the University of Valencia, my group here, the funding of supporting these studies, and finally, most importantly, Antonio Carlos Borin for inviting me for this, giving this webinar. Thanks also to you for listening. Thank you.
Thank you very much, Daniel. Very nice talk. Very nice. Any questions? No? Well, there is one from me. Daniel, you said you select around 100 snapshots for the quantum mechanical calculations. I mean, for the excitations, energies, and oscillatory strengths. Okay?
Between 100 to 200, we have done several tests also. So increasing the number of geometries. Yeah.
Okay. And how do you select these snapshots?
I mean, this is randomly. So it's a procedure. We create a Wigner distribution, or I mean, it can be Boltzmann distribution, Wigner distribution, and then randomly we select these geometries. I mean, based on not exactly randomly, but based on the distribution function.
Okay.
I mean, it's weighted by the distribution function.
But when you do the molecular dynamics calculations, you select some snapshots too,
yes,
or not?
Yeah, exactly. So for the sampling of the solvent, so what we do is a long molecular dynamics. So we equilibrate the system, and then when you are in the production zone, that is called, so there we take 100 or 200 of geometries separated with the same time size. I mean, for example, each 300 picoseconds or whatever, yeah. So we do some of them, yeah.
And when you the number of solvent molecules, I mean, in your case, it was water. In the very first, I think it was in the first example you showed us. And do you select the water based in the solvation cells, the number of water in the first solvation cell, for instance, or?
Wait, but sorry, I didn't get your.
You have select some water molecules, for instance, to place around your chromophore, okay?
Yes.
And I mean, how do you select the number of water molecules to place around your chromophore? Based on the
you mean in the case of the acrolein or in general?
In general.
In general, well, if you have, I mean, you can do several tests using quantum chemistry or also running molecular dynamics to see what are the molecules that have a stronger interaction with your chromophore. Also, mainly, if you have the possibility of forming hydrogen bonds, then surely I take those solvent molecules that can have hydrogen bonds with my chromophore. So it's based on many things, from molecular dynamics, from computations with DFT, and also considering this fact that you can form hydrogen bonds, and then these are going to be the strongest interactions.
Okay, that's it. And how many excited states do you include in your, do you normally use? I mean, how do you know that it's enough, for instance, 3 excited states or 4 excited states?
Well, you can do a test also. So depending on which is the window of energies that you are interested in. For example, in atmospheric chemistry, if you are interested in the troposphere, so you will consider those transitions that are at higher wavelengths than 290 nanometers. This is the main the solar irradiation that arrives in the troposphere is this one. No? If you go to the stratosphere, you consider also higher energies up until 200 nanometers. So it depends on your interest, no?
Okay, you include as many excited states as you have that energy range.
Yeah, exactly.
Okay, thank you. Any other question, please?
Yes, I have a question.
Danilo?
Dear Daniel, nice talk, very interesting. In your talk, you mentioned the ASEP approach. If I'm right, you perform one quantum chemistry calculation in this approach using sequential QMMM. method, right?
What you said at the beginning?
Yes, average, solvent, electrostatic protection.
Okay, yes. But I'm not using this one. I was just introducing as an example of a strategy that you can use to deal or to compute the interaction between the environment and the chromophore. But I was not using that.
Okay, no, okay. Because in this case, it's cheap, this approximation. Okay.
So it was just an example of methods that you can use or strategies that you can use to treat the interaction between the environment and the chromophore. That's what I was trying to say. Yeah.
Okay, right.
Any other question, please? Orlando, do you want to talk? To ask something?
Sorry?
No, there is another friend of mine, Orlando. He's writing in the. Okay. There is another one, Victor. Okay.
Yeah, just a curiosity. When you were comparing the Wigner sampling with molecular dynamic, I saw that the Wigner sampling has shoulder, and it's almost a second peak for the material studio result. Is this irrelevant, or can you talk a little bit about this?
No, no. To me, it's not relevant. I think this is probably we need more geometries probably to change this, because it means that probably we need to compute more, to explore more the conformational space of both the chromophore and the environment to have a much better approximation, no? Because it's not appearing in the amber also. So and we are working there. I mean, we are simulating there only one type of excited state, is the n-pi star, and the other excited states are far enough. So it's not that this shoulder is coming from another excited state. So it's from the same excited state, but due to the approximation that I'm using, we are not able to create a good resolution of the band. Yeah. So I'm not significant.
Okay, thank you.
Any other question, Eric? Okay.
Let me say that I mean, I think maybe it's not clear. Let me add to this question that the approach is not able to determine the vibrational structure of the electronic bands. So it's only able to produce the shape, more or less, and the position, energy position, and more or less the intensities. But we are not able to obtain any information from the vibrational structure of the band. That's I mean, in order to do that, you need to go to other approaches like quantum dynamics, or the approach that I was also introducing based on normal modes, no? To compute the vibrational structure of the ground and excited state. That way, you would obtain information about the vibrational resolution. No? But with the approach that I showed here, no, you cannot get further information.
Okay. So can you say that the position of the maximum would be somewhat important when you're comparing these different sampling strategies?
I care. Well, when I have a strategy that is able to produce the whole band, what I care is about the band. I mean, the whole band, not the maximum, or I mean, in general, the shape, basically.
Okay. Thank you.
Yeah.
Hi, Daniel. Great.
Hello,
Thanks
Eric.
for the talk.
Yeah.
Maybe I will give you. Sorry.
Yeah. Tell me.
I have two quick questions. The first one is about the luminol system.
Mhm.
So what we know about it is that the mechanism in water is different from the mechanism in DMSO. So the formation of the excited state maybe follow a different path, because in DMSO, what you have is an auto-oxidation with molecular oxygen, and in water, you need some kind of oxidant, like hydrogen peroxide or something like this. So in your opinion, the final result is that you get the kind of same mechanism of chemi-excitation, but maybe a different mechanism to get to the high energy intermediate? Is that correct?
Yes. As far as I have research on that, I mean, luminol is quite complex, the luminol chemical process. So still many unknowns still. But as according to my research, what I see is that the crucial species for chemical excitation is this monocyclic endoperoxide you have, and this species will be the same in a water solution or dimethyl sulfoxide. So in the same species. Then the difference that I see here is that in the excited state, in dimethyl sulfoxide, there is a proton transfer, and you produce a iminoform that is the responsible for light emission in these conditions. In water, this is not happening. That's the difference between water and DMSO in the excited state after the chemi-excitation process. Of course, I agree with you that before forming this monocyclic endoperoxide, before the chemi-excitation, the reactivity is going to be totally different. And the effect of the catalysts and the species that are responsible for in water and DMSO are going to be different in the previous steps. So that's what I see from my research. That's my knowledge that you have.
The second question is about the determination of the molar absorptivity coefficients. And you know, I know nothing about calculations. I'm an organic chemist. I work with experiments, but I know a little bit about what we can and what we cannot do with calculations and with experiments. So I understand the limitations of in terms of size of the system that you can calculate. And therefore, I understand that it's impossible to consider aggregation effects and other effects that you see when you are measuring a real sample. But I know that usually only the first layer of solvation is responsible for the most important electronic effects that determine the shape and the intensity of the absorption spectra. So what happens if you change the size of your periodic box if you are using the explicit solvation and also implicit solvation using a PCM model or something like this?
Yeah, I think, for example, I agree with you that the box, for example, the size of the box that I use probably is too large, no? Probably you can reduce much more and focus only on explicit models, solvent molecules around the chromophore, and then using implicit model for the other. So this would be also a good approach, but not only the first solvation cell. I would consider, I don't know how many molecules, how big should be. It could be tested also, but not only the first solvent shell. You need to capture all the dynamical effects of the interaction between the solvent molecules and explore as much as possible the conformational space of the solvent. And then if you only use the first solvation shell, this is not representative of all these dynamical and statistical effects of solvation. So I cannot answer you how big should be the box, but I agree that, maybe the size of my box is too large, and it can be reduced and then using PCM. But for technical problems in computations, using periodic boundary conditions is not introducing computational effort. So, I mean, of course, what is introducing the computational effort is everything that is included inside the box. That's true.
Daniel, thank you very much. Great talk. It is good to see you again, and your work is very, very beautiful.
Yeah, thanks. Long time ago that haven't seen you. Long time ago.
We need to get together, have a beer, maybe in Spain or in Brazil, as soon as the coronavirus crisis ends.
Yeah. Let's see. If you are coming to the, I think, to the Chemiluminescence Symposium, maybe it's gonna be organized next year, but not sure still. No. So hope to see you soon. Yeah. Good.
Any other question? No more questions? So I thank you again, Daniel, for a very nice talk. And nice to meet you again, to see at least again. Yeah, it's terrible, but that's the way you have to live nowadays.
Yeah.
Okay.
Let's see with the machines now.
Okay.
Yeah. Good. So thanks to you, Antonio, for this invitation. It's always nice to talk to you and your friends from there. Yeah, always nice.
You are always welcome. You and everybody from Valencia. Okay. Good. Thank you very much, Daniel, and I hope to meet you again soon. Okay. Good. Thank you, everybody, for being with us this afternoon. And this is the last seminar of this year. And we are going to restart next year in February. Okay, I have already 2 more seminars arranged for the next year. I'm sure you are going to enjoy them too. So thank you very much, and have a nice evening, or have a nice night for you and Javier in Valencia and everybody in Europe. Thank you very much, everybody. See you soon. Bye-bye.
Thank you. Bye-bye. Thank you.